point, I assigned two assignments, project number 1 and the quiz number 1. Okay, yeah. All right. But today is the deadline for quiz number 1, right? Yeah, today. Remember, everyone. But I try to give you quiz number 2 tomorrow. Tomorrow, okay? Yeah. All right. Module 2, the topic, analysis of algorithm efficiencies and a brute force method. Yeah. Part A, problem solving from experience and elimination method. Yeah. 8.1, selection sort. First, let's look at our computing problem number 4 for this class. Sort and array. Question, given an array with n elements, how to sort it in ascending order? So it is a basic question. Remember, we have 3 basic types. Search, we did a linear search, right? Selection problem, we did finding the minimum problem. Now, the first one in sorting category, sort and array. Yeah. So today we look at the first one. In this class, we may need to study about 6 or 7 sorting algorithms for this class. Yeah. So this is the first one. All right. So yeah, the problem type, yeah, and reference section 3.1. All right. First, let's start with analysis. What idea? What's the basic method we like to use in our first solution? Yeah. Here we take, in our problem solving, it is very common when we need to find the solution for a new problem, we want to connect to our experience, to our existing experience. Otherwise, we do not have any idea. So if we can connect to our experience related to this problem, probably we can borrow some idea. So here we need to connect to our experience. Our experience is module 1, because we only learned module 1 at this point. So that's how much you can connect. All right, yeah. All right. And we need to explore properties. Here, when you try to understand the problem, you need to explore some useful properties. So we did a few examples before. Properties, critical properties. Here, we also need to do the similar thing. All right, yeah, so that's the basic guidelines for problem solving.
Jesse.
Oh, Jesse, all right, yeah. Yeah, I need to write somewhere. Yeah. Yes. All right. Backward thinking. Yeah, another commonly used technique or thinking method in problem solving. Backward thinking. Yeah. So I think you know it. You can assume the problem has been already solved. then you try to, get some interesting properties. You look at the problem from the backward, already solved. So you get an ascending array. After you do some data processing work, you get the array sorted. All right. So now you want to see some interesting property. All right, yeah. What property can we discover if it's already sorted? Yeah. Here in this sorting, although in the given problem description, we do not say the elements are distinct. Yeah. But in our first version of solution, we can assume distinct elements. Because in this way, we can simplify. So make our problem as simple as possible. So you do not need to consider the equal case. Two elements could be the same. So you can reduce the discussion. Now, but after we find a solution for the distinct elements, then we consider the general case. You only need to modify your solution slightly to include general case. Yeah. All right. So how to connect this problem to the minimum problem? Yeah, because based on our experience, we learned 3 computing problems. The first one, evaluate polynomials. Second one, linear search. Third one, minimum problem. So which one you can borrow some idea? It's most likely the minimum problem. Yeah. Now we try to connect to the minimum problem. Yeah. All right. Let's do some observation. Let's draw a diagram. Yeah. Backward thinking, we assume the array has been sorted, so it's an ascending order. Now, can you tell me some interesting property related to the minimum problem from that diagram? Yeah. Can you connect to that minimum problem? Backward thinking? Yeah. Or I ask you a question this way. Here, we assume we can find the solution of the minimum problem. Yeah. So every time given an array, you can find its minimum. All right. You have it, the minimum. All right. Can you use that minimum in the array to help you get some useful information there? That's the question. Yeah, the minimum. Anytime you can get a minimum easily, can you use that partial solution? Yeah, let me call partial solution. Use that partial solution to help you do something useful there. That connection is important. Yeah. All right. What is the minimum in this array? What is the minimum in this array? Because it's already in ascending order. The minimum is the first element, right? In ascending order, right? Yeah. Now, because we can find the minimum anytime. That means the minimum we just found, that should be the first element in the destination array, right? The minimum we find, it must be the first element in that destination array. How about that? This simple observation. Okay, yeah. So if you see this relationship, connectivity, then you're almost there. You will get a solution, you know, pretty much there. All right, yeah. Okay, yeah. So here you can see we apply the minimum problem solution. We can locate the first element in the destination array immediately, A0. That's the minimum. That's the first minimum. Yeah, let me call the first minimum. Okay, yeah, because after we locate the first minimum, next round, yeah, because we need to do more work. The next round, we can exclude the first element, right? Yeah. We don't need to touch it. We can exclude it in our consideration, right? All right. So here, in order to facilitate the discussion, I like to introduce a concept called in-place concept. Yeah. Simple. So you know the meaning. Yeah. Here, I just use this concept to describe that A0 element. We put it in place. After the first round, we find the minimum. We get first element in place in our destination array. It is in place. We put it in place. Yeah. That means if we look at a destination array, it is at the right place, right? Right location. No. The final location. A0 is at its final location already. Okay. So the next round processing, we can ignore A0. We can eliminate A0 in our consideration. So we can reduce the problem size. Yeah. So the next round, think about the next round. Second round, we apply finding the minimum solution on the remaining elements of the array. What will you get? Second minimum, right? Yeah, you can call second minimum. Second minimum, it corresponds to A1, and we also put it in place, right? Yeah. So the second time you apply finding the minimum solution, you put the second element in place, and so on. Yeah. So every time you put one element in place, another element in place, and so on until you put all elements in place. How about that? That's the idea. That's our first solution of this sort problem. First solution. Here we do not say good or bad. Yeah. Just a solution. Later we will discuss if it's good or not. First one, it's a valid solution. It is correct. But here I like you to look at the whole procedure from problem-solving point of view. For this class, I like to give you a good training of problem solving. When you are given a computing problem, how to do analysis, how to apply some thinking methods to find a solution. Yeah. So let me summarize this whole procedure. You need to have some problem-solving background. Otherwise, you cannot go very far. Okay? So you have to have some basic background. Yeah. Here, our module 1 is our background. Okay? So we do not have much, but we have a little. Module 1, 3 computing problems in module 1. That's our background. Okay? Yeah. Fortunately, we can find the one that can be used here. That's the finding the minimum problem. That one can be used here. Okay? Yeah. So we use that. We apply the solution multiple times. Right? Multiple times. Here, I like to ask you how many times we apply that minimum solution. How many times do we need? We apply that solution certain number of times. Can you tell me how many times we need to apply that solution? Yeah. Good. It's a good guess. Yeah, I want to say it's a good guess. All right, but it's a guess. So we want to really make sure it is correct. Next step. First, we get a close guess. Okay, yeah. Now, N is very close, but can we fine-tune it to make that correct answer? N minus 1. N minus 1. Let me tell you why we can cut 1 off. The last one, we do not need to apply it, right? Think about it. The first time, second time, third time, when you apply N minus 1 times, you put N minus 1 elements in place, right? Then only have 1 element left. You do not need to apply another time, because only last position left. That's the only place you can put the last element. You can save 1 function call, right? Yeah. Yeah. So here, although that 1 function call is not a big deal, yeah, but here we want to do our analysis accurately. Okay? Accurately. Yeah. All right. So that's the answer. We apply it N minus 1 times. Then we can put all elements in place. That means we get a whole array sorted. That's the whole procedure. Some of the views we can apply again later, because later when we solve this problem in different ways, we need to put all elements in place. All elements in place. All right, yeah. So that's the, yeah. So the elements is play, yeah. So here the definition, yeah, of this in place. Now, meaning, okay, yeah. Later in our discussion, we will use this term, yeah. But later, after some time, we will use this in place term to describe algorithms. In place algorithms. At that place, the meaning will be different. Here, I just let you know, yeah. There are 2 different meanings for this in place in this class. Yeah. First one, we talk about in place elements. You know the meaning. So that's the, direct, based on your natural understanding. But second, we do not describe elements. The second one, we describe algorithms. We call the in-place algorithms. Yeah. So I will talk about that later. So do not get confused. Yeah. Some students get confused. All right. All right. Also, we apply elimination method a little bit. Yeah. Although not too much, because every time we eliminate the in-place elements, that's how we apply this elimination method. In-place elements. Yeah. All right. Okay. Yeah. So we finished that discussion, but we need to do efficiency analysis here. Yeah. So let's go through the procedure again, but this time we need to count the number of comparisons. How many comparisons do we need to sort this whole array? Yeah. All right. So the first time, yeah, each time we find one minimum. Yeah. But finding each minimum, how many comparisons do you need? Think about that. Okay. All right. Yeah. So let's do the counting. Count the number of comparisons. Yeah. The first time you need n minus 1 comparisons. All right. Second time you need n minus 2 comparisons, n minus 3 comparisons, and so on. Yeah. Second to last one, 1 comparison. Second to last one, 1 comparison. Okay. Yeah. The last one, 0 comparison. Okay. Now you add up all these numbers, you get this 1/2 times n minus 1. That's the final answer. This many comparisons. Okay. All right. Then let me ask you, what is the best case? What is the worst case? What is the average case efficiency? We have 3 different efficiencies, 3 different types of efficiencies. Yeah. So in this question, what are those numbers? Best case, worst case, and average case.
Really, the best case would be if they're all equal. All the elements are equal.
Even if all equal, how many comparisons do you need?
4 n minus.
All right, yeah. But actually, it's a good question. Although the answer is incorrect, but you reveal some common mistake. So I like to talk about that. All right. First, let me tell you the answer. Even all equal, all the elements equal, answer still this number. Still this number. Okay? Yeah. Because your computer algorithm does not know all these elements equal, right? You need to go through that for loop, you know. All the lines of your code should be implemented, right? Even all numbers equal, your computer does not have eyes. Your computer do not treat your computer as ourselves. Okay? We can see all elements equal, right? The computer cannot see. Computer does not know all elements are equal, right? So you enter all equal elements, but computer still does the execution line by line from beginning to end, executes the same code. Then no comparisons saved. No comparison saved. All right? Yeah. Yeah. So your computer, you know, we know computer is powerful, but still sometimes do not treat computer too smart. Computer cannot see anything. Okay, just blind. If you want to do detection, yeah, you need to put in your code to do detection. Okay, here we do not have detection code. So the computer does not check if all the elements are equal or not. Okay, you need extra code for checking, but if you put extra code checking equal or not, too much work. Because the probability to have all numbers equal too small, too little, not worth it, not worth the checking. Most of the time, 99.999% not equal, but you still do the checking. Think about that. If you do the checking, too much work, not worth it. So that's why we never do it. We never do the checking, not worth it. Okay, redundant work. Probability too small. If the probability is high, 50%, then worth the checking. Okay, but the probability is 0.00001%. No, don't do it. Okay. Yeah. All right. So this kind of thing, useful experience. So in your coding, you do not do redundant, unnecessary work. Yeah. Only do the necessary work. Yeah. All right. Let's continue. Answer for this question. All these three cases answer the same. Why? Because we only have one case. This is the only possibility we have. Think about that. We do not have second different case. That's all the possibility we have. Only one. Only one. No matter it is elements equal or not. That's the only one possibility. One case, that's the best case. Worst case, also average case. All right, so we finish discussion of this topic. Okay, then summary for this elimination method. Yeah. This idea is simple, but it is very important. And in this class, we need to apply this elimination method many, many times. And sometimes you will see we need to use this simple idea to solve some very challenging questions. Very challenging questions. Here, let me give you the basic idea, the goal. Why we apply elimination method? The goal, reduce the problem size. If you can eliminate as many elements as possible for the consideration, you reduce the problem size. Okay, yeah. And we know the smaller the problem size, the easier the problem. So this statement, look at this statement. Here, I want to discuss a little bit about this statement. The smaller the problem size, the easier the problem. Oh, the easier the solution. Yeah, let's say this way. Okay. Yeah. The easier the solution for this problem. Okay. Yeah. Now let me ask you this question. Do you agree with this statement? Do you think this statement is correct or not? Yeah. Something interesting here. Do you feel this statement? So how do you feel about this statement? Yeah. Something interesting I want to discuss. Yeah. Otherwise, you may use this statement in a wrong way. Yeah. Wrong way. Use it in a correct way, not wrong way. All right? Yeah. So that's something very important. All right. the first thing, problem size, this concept. Do you want to ask question, what's the meaning of problem size? Right? Yeah, you have some idea. Yeah, but when we talk about problem size, usually there are two meanings. Problem size. Usually there are two meanings. The first meaning, number of elements of the data. Array, data. Yeah. So that's the most commonly used case. All right. But there is a second case, not that common, but another important case you need to consider. The magnitude of a number. We also call the problem size magnitude. You know magnitude, right? How large it is. Is the number big, small? That number, how large it is, we call the magnitude of that number. Sometimes we treat that magnitude meaning as the problem size. For example, let me give you the example. What's the example? The magnitude example. We do prime factorization. We do prime factorization on an integer. In this case, we only have one number, one large number to be factorized. One number, so you cannot use that one as the problem size, right? The magnitude, the value, how large is the value? That one is the problem size. Okay, yeah, magnitude, all right, yeah. So when we talk about problem size, basically these two different cases we consider, okay? All right, now let's back to this statement. The smaller the problem size, the easier the problem. How do you feel about this statement? How do you feel about this statement? Can you say this statement is 100% correct? Always 100% correct? Can you say that? No, right? No. If you use the second meaning of problem size, magnitude, can you say the larger the magnitude, the harder the factorization? Can you say that? No, right? 1 billion. What is 1 billion large? If you do prime factorization on 1 billion, is it easy? Very easy, right? 1 billion. But if you do not as big as 1 billion, much smaller than 1 billion, but 3, 5, 7, 2, 9, 8, 7. This number is smaller than 1 billion, but if you do prime factorization on it, it is very hard. Okay? Yeah. So you can see this statement is not 100% correct. Okay? Not 100% correct. Okay? All right. But why I put it here, right? Well, why, if it's not 100% correct, why I put it here? Okay? So the reason I put it here, we call this is a principle. When we say a principle, generally it is correct. Generally it is correct. Okay? Yeah. So why we get a principle? The reason we get a principle, we want to use it to guide us in problem solving. Yeah. We want some useful principle to guide us to find a solution. Guideline, principle, guide us. All right. So this principle is useful to guide us to reduce the problem size to make the problem easier to solve. Yeah. Based on this principle, we try to reduce the problem size to make it easier to solve. That's the reason it is useful. Yeah. Otherwise, we won't reduce the problem size. Yeah. If you feel this statement is incorrect, we won't reduce the problem size because we feel useless. But actually it's useful, right? Reduce the problem size. Think about that. Okay? Yeah. Actually, the problem size reduction is a main topic in this class. We always do problem size reduction to make our problem easier. That means in general, it's correct, problem size reduction. Okay? There is some special cases it's incorrect, but that percentage is very small. Okay? That percentage is very small. Yeah. So we do not worry about it. Okay? We do not worry about that small percentage case. The statement is incorrect. When we encounter that situation, then we consider different ways, different ideas. Yeah. But in the general situation or normal situation, we can apply this principle. Okay? Yeah. So here, let you know, use the statement in the correct way. Okay? In the correct way. Yeah. All right. When some elements do not change the outcome, if you, after you do some work, analysis work, yeah, typically we do comparisons. After you do some comparisons, so you collect a lot of useful information, then based on your analysis, you can determine certain number of elements. They won't change the outcome. Then you can safely remove them from the consideration. Then you only need to consider fewer number of elements. Then easier, you need less work. That's the main idea of this method. Very simple, straightforward, yeah. But sometimes very effective. Sometimes it's quite effective. But for people, if you do not have the training of this elimination method, you may not be aware of it. Okay? Although you can eliminate many elements, but you may not be aware of it. This idea. Okay? You still work on large number of elements. When you work on large number of elements, you do some redundant work. You may do some redundant work. Okay? Yeah. You can eliminate half of them, but you still, if you do not eliminate half of them, you still do a lot of redundant work. That's the point. That's the reason we want to eliminate as many elements as possible. So you won't do redundant work. That's the main idea of this method, elimination method. Okay. Yeah. Later I will give you many examples. Many examples. Yeah. You need to solve. Yeah. In your assignments, in your tests, you will have many questions using elimination method. All right. 8.2, impact of organized data. Second topic. Yeah. All right. Let's solve problem number 5, element uniqueness problem. From the title, you can guess a little bit. So what we are going to do? Element uniqueness problem. You need to detect, given an array, if the elements are unique or not, or if any element is repeated or not. Okay, yeah. So what's the best way? What is the best solution for this question? Yeah. Given an array with n elements, how to check if all the elements are distinct? Yeah. If all the elements are distinct, return true, Boolean value true, your function. Otherwise, false. Not unique. Some duplicate elements, then false. Yeah. So now we need to think about the solution. Yeah. How many comparisons? How to do our comparisons to find a solution. Yeah. All right. So here I like to use two methods. Two methods, because I want to convey a point. Remember the title, impact of the organized data. I want to convey the point. Importance of organized data. Okay. Method 1, brute force method. Method 1, we do not do anything special. We just do comparisons immediately on our data from beginning to end to check if any two elements have the same value or not. Simple. No. Yeah. Do nothing to organize data. Okay. Do comparison immediately. That's the first method. Yeah. No cost on organizing data. We do not spend any cost, pay any cost. We do not pay any cost to organize data. Okay. Yeah. So in that sense, no cost. No cost in data organizing step. Okay. Yeah. All right. Yeah. So let's consider this special example. Yeah. Here, special example. In order to check this array does not have duplicate element, how many comparisons do you need? You need to do the checking from beginning to end. Yeah. The first time when we look at if the first element is repeated or not in the array, yeah, we just want to know if 0 appears anywhere in the array. So we want to do all possible comparisons to get, we need to do n-1 comparisons, right? Remaining n-1 element, we want to see if it also appears in one of the remaining n-1 locations. So that's for the worst case, n-1 comparisons. The best case, you do not need n-1, right? Best case, one comparison. The same, return false, right? Yeah, distinct, return false. You're done. Yeah. For worst case, you need to do all the possible comparisons, n-1. All right. How about second element? 1. You want to check if 1 appears in the remaining. You do not need to look at the 1 before it, right? Yeah. You only need to compare 1 with all the other elements after this position, not before this position. After this position. Before this position, you already did it. You did it before. Okay? So after this position, n minus 2. Okay? Yeah. Next one, n minus 3, and so on. Okay? Yeah. All right. Second to last, 1 comparison. The last one, no comparison. Okay? All right. Yeah. Now you can see for the worst case, how many comparisons you need for the worst case. Not best case, worst case. Okay? All right. The best case, easy, right? Yeah, the best case. This is the best case. Okay? 1 comparison. Best case, 1 comparison. Okay? Yeah. For the worst case, yeah. Worst case. Yeah. All right. Here, I give you the special data, special array for the worst case. Yeah. This one also for the worst case. Worst case, you need to add up all these numbers so you get 1/2 n times n minus 1. That's the worst case. Okay? Yeah. 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 Here, I do not ask you average case. Yeah. I do not ask you average case. Yeah. All right. It's not easy to answer. Yeah, you can think about it. Not easy to answer. Yeah, because you need some probability assumption. In order to represent average case accurately, you need some probability assumption. Yeah, so for that reason, I do not ask you, okay, this question. All right. Yeah. Yeah, so the average case, yeah, you can think about, yeah, but I won't give you in any assignment. Yeah, just think about it. Okay. Yeah. All right. Yeah. But this is method 1, brute force method. Yeah. Now I want to talk about method number 2. But this time we will pay for some cost to organize data. Okay? We want to do some work. We want to do some investment. Yeah. So this cost pay, the cost we pay here, we treat it as investment. Because we will enjoy the result. Yeah. We pay for something useful, valuable. So we will enjoy them. You know, some good property we can get from this investment. Yeah. So that's the idea. Okay. All right. Method 2, investment in data structure. Yeah. When you apply some better, more efficient data structure, it's not free, right? Data structure, useful data structure is valuable, but it's not free. You need to pay for it. Okay? Yeah. So we sort the array first with certain costs. When you sort, you need to do many comparisons to sort it. Okay? That's our pay. That's our investment. Okay? Yeah. All right. So here, at this point, because we haven't learned much in sorting, so here I just give you the best we can do in sorting. That's n log n. Yeah. So we will get this formula later. Yeah. At this point, we do not have this formula. Yeah. But when we do the sorting, it's very easy to get a sorting algorithm that gives us n log n efficiency. efficiency number, n log n. Okay, yeah. Later we will derive this formula. Here we just borrow the formula. We can do the sorting with n log n number of comparisons, approximately, okay, approximately. So we're fine to use approximate formula. Yeah, all right. Yeah. The question, how to check if any elements is repeated in an ordered array? Yeah, after we pay this much cost, now we enjoy the good property we get because we have an ordered array this time. In an ordered array, when you need to check if any element is repeated, is it easy? Much easier? In an ordered array. Okay, think about that. Think about that. In an ordered array, to check if any element is repeated, how many comparisons do you need for the worst case? For the worst case, how many comparisons you need? Good. That's a perfect answer, n-1. Yeah. I think you get better and better. Yep. All right. So the reason very simple. You only need to do adjacent comparisons, right? You only need to do adjacent. Every time when you just compare two adjacent elements. All right? Two adjacent elements. When you do comparison. Okay? Because after the sorting, if there are two elements with the same value, you will find from two adjacent comparison, right? Yeah, yeah. Because all the elements with the same value are one after another, back to back. Think about that property, that observation. So if you do adjacent comparison, you will find it immediately. Okay, now you can see we only need n-1 comparisons. So the code is also simple. Yeah, n-1 comparison is sufficient to check if there is any repeated element. Okay, yeah. Now, because we pay this investment n log n, we paid before, okay? Yeah. Now we enjoy the result. We only need n-1 comparisons. Yeah. If we do not pay that investment n log n, then we need to do global comparisons, right? Yeah. When you compare two elements, it's a global comparison. It's not local comparison. It's not adjacent local comparison. It's a global comparison. For the global comparison, you need to consider all the possibilities. That number is big. For the local adjacent comparisons, you reduce the number of possibilities greatly. That's the reason you can do faster. That's the reason you can do faster. Here, you know, sometimes we are willing to pay, you know, at the beginning for data arrangement, yeah, because we will benefit from that investment. Yeah, this is an example. You can see. Okay, all right, yeah. So these two methods. The second one is better than the first one. Yeah. Why the second one is better than first one? Yeah. Because remember, you need to add this n log m, that cost, you need to add it back to the total cost. Now, even with this n log n you paid before, you get a better overall efficiency. Yeah. But that one, I will talk about in part B. Yeah. Part B, so when we compare two growth functions, then I will use rigorous math to show you the second one is better than first one. Yeah. Today, I do not do that, because today I do not have that much time. So I delay to next time. Yeah. Compare two growth functions next time. Yeah. All right. Yeah, but here, before we finish the discussion of this question, I want to stretch a little more. Yeah. We can do, if we use advanced data structure, we can do better than this one. This method number 2, we do better than method number 2. Yeah. Actually, this simple, this problem number 5, element uniqueness problem, it's a simple one, right? Yeah. But this kind of algorithm questions are frequently given in job interview. So many companies, actually many famous companies, so not the small companies, top tier, those top tier companies, they need to give tests to their candidate, usually algorithm tests. And this question is frequently given in their algorithm test. So what's the fastest method to check if a given array, if the elements in a given array are unique or not? Okay, yeah. So the first one, second one, although these two methods, should not be a good solution. Now I want to talk about the third one. If you give the third solution, then it will be the best. Okay. Third solution relies on another advanced data structure. So here, let me give you a name. Yeah, I will talk about this data structure near the end of the semester. So I just give you here. It's called hash table. Hash table data structure. Okay, hash table data structure. So here I do not want to describe hash table, because today we do not have that much time. Okay, so we in our module 5, module 6 probably. So we will talk about hash table. All right. Here, just tell you this hash table. Given array, we build a hash table using the elements in the array. Hash table. How to build, hash function. We need a hash function, to map the array index. Okay. Array elements. All right. We build a hash table. But when you build a hash table, if there is any element repeated, then you will find it, because there is a collision. Okay, hash collision. When a hash collision occurs, the elements is not unique. And when you build, the cost you pay, big O of n. This big O notation, I will talk about in next class. Big O of n. Okay, here you just know some linear constant times n. Okay, linear constant times n. Then it's much faster. You just go through the array, but you need to put it in a hash table. Okay, you need to insert in a hash table. All right, but if one element is repeated, you get a collision. Because when you insert, you will hit it. You will hit an existing element in the hash table. Then you find it. That is the fastest. That is the fastest solution. Okay? Yeah. Yeah. But you need a hash table. You need advanced data structure hash table. Okay? Yeah. Yeah. All right. Yeah. Any question so far? Yeah. All right. I have 10 minutes. So now I want to talk about one question in project number one. In project number one. Yeah. I post the description. Yeah. I hope you look at it a little bit. Yeah. But here I like to talk about the overflow problem. Yeah. I'll give you the description, overflow problem in the, I put one paragraph to describe that overflow problem. Yeah. Right. So that overflow problem could occur in our computation. Okay. Overflow problem could occur in our computation. Yeah. The problem is no complaint. No complaint from the computer. That means even if it occurs, you do not know it. Okay? You do not know it. Then how do you know your answer is correct or not? You may not know. You feel your answer is correct, but actually it's not, because an overflow occurs. And there is no complaint, so you do not know it. That's something I want to point out in this project. So you need to know it, okay? Yeah. You learn, you need to know there is this problem. Yeah. But when you submit your project, you do not need to tell me anything, okay? This overflow problem. Right. So here, just for learning experience, for you learning. So you know, we do something to avoid overflow. Yeah, because in our project design, we avoid overflow. So you just understand why overflow could occur. Okay, try your best to avoid it. Yeah, but in your output, you do not need to show me anything. Okay, yeah, yeah. You do not need to show me anything. Yeah. All right, but here I want to explain this a little detail for this overflow. Why overflow occurs, right? Computer does not complain. How do you know the overflow occurs? All right, yeah. In our project, I give you a special polynomial like this. Square. Okay. I define special polynomial to help you expose the overflow problem. Yeah. It's hidden, but we try to expose it. All right. And this function, we know, it always gives us positive values for x positive. How about that? Yeah. We just take x positive numbers, then this polynomial should give us positive numbers, right? Yeah, because we never do subtraction here, always addition. We can always get it bigger, not smaller. Okay, yeah, all right. Then I tell you, you can see some absurd output if you try this. Okay, if you try n equals 25, x equals 123. Okay, yeah. But here, for the data, you use long integer data type. Okay. Oh, that's bad. Long integer type. Yeah. Then, why we find overflow? You will see after you plug in these numbers, you do the calculation, you will get P25 123. You will get a negative number. Oh, that's bad. That's the problem. At the end, it becomes because near the end it becomes very slow. Yeah, but the problem is how to control it. Yeah, I just want to say a few words. All right. Yeah, because we know this function cannot be negative, right? If it gives the negative value, it must be wrong. It must be wrong. Okay. But the question is, why this polynomial give us negative value? Okay. Why? Yeah. All right. So here, let me give you a quick answer because we don't have much time. Let me give you the quick answer here. Yeah. All right. Still a few minutes. All right. All right. Remember that long integer. First, you need to know the long integer. Long integer use 8 bytes. 8 bytes. Yeah. Oh, stop sharing. Long integer type. Yeah. Then, why we find overflow? You will see after you plug in these numbers, you do the calculation, you will get P25 123. You will get a negative number. Because we know this function cannot be negative, right? If it gives the negative value, it must be wrong. It must be wrong. Okay? But the question is, why this polynomial give us negative value? Okay? Why? Yeah. All right. So here, let me give you a quick answer because we don't have much time. Let me give you the quick answer here. Yeah. All right. Still a few minutes. All right. All right. Remember that long integer. First, you need to know the long integer. Long integer use 8 bytes. 8 bytes. That's 64 bits. 64 bits. Okay. Yeah. For the 64 bits, the highest bit is used as the sign bit. Sign bit for the sign. Okay. sign bit, that means 0 means positive. 1 means negative. So the highest bit is the sign bit. All right. Now, you do computation, okay? Yeah. You get overflow. You reach, when you get overflow, that means your output number could be represented in more than 64 bits, right? It could be more than 64 bits. If more than 64 bits, computer does truncation automatically. The computer only takes the last 64 bits, okay? The bits before 64 bits, that part truncated. Throw away, okay? Throw away, truncated. Only keep the last 64 bits, okay? Yeah. But if the highest bit happens to be 1, you get a negative image. Highest bit is 1. It's possible. After truncation, it is 1. Then it's a negative number. So what do you see is a negative number? That's ridiculous, right? It cannot be negative. So you know something is wrong. So you find the overflow. Otherwise, how do you know the overflow? Yeah. Think about if the output is positive, do you know it's overflow? If the output is still positive, do you know it's overflow? You don't know, right? Yeah. Here, I tested. Yeah. If you like to write a program, do experiments on this polynomial, test. I did testing. I just changed n equals 26. I still use x1, 2, 3. I change n to 26. This number should be larger, right? Larger than 25 case, right? But that time you get a positive number. You get positive number, but it must be overflow, right? Because at 25 you get an overflow. At 26 you get a larger number, you even more overflow, right? But after truncation, you get a positive number. How do you know you get overflow? It's positive. How do you know it's an overflow? You don't know it's an overflow, right? Yeah. So this tells you in the real world situation, sometimes you don't know why, but the answer is wrong. Okay? This gives you one of the typical situations you may have in the real world situation. Okay? All right, so that's it.